Hello, welcome. This is lecture number 24. What we will do is we introduce the concept of conjugate beam method in the last two classes. Today we will see some example. Okay, the first example is so today's first example is this example, cantilever beam subjected to tip load. You remember in the last class through this example we demonstrated that the conjugate beam is just not the applying the force on the conjugate beam as bending moment diagram, EMI curvature diagram of the real beam. In addition to that, you have to take care of support as well, because if the supports are not supports of conjugate beam is not chosen properly, then it may give you a wrong result. So, in the last while demonstrating that, what we did is we kept the beam as it is, but did not change the support at this point and at this point. Okay. Now, let us see this example once again with applying the entire the both loading and support of conjugate beam. Okay. Now, first draw the bending moment diagram of the beam. The bending moment diagram becomes like this. This cause hogging in the beam. So, bending moment will be negative, and this is PL, and this is P into L minus X. X is measured from A. Okay. This is bending moment diagram. So, now let us draw the conjugate beam. Conjugate beam is length of the conjugate beam remains same. This is the length of the conjugate beam, and the loading on the conjugate beam is this diagram divided by EI. So, this is acting upward because bending moment is negative. This we have seen in the last class. Okay. Now, so this is P L x minus, this is P L minus x divided by EI. Assume EI constant for this beam. Now, if you recall this table, if the fixed end in real beam becomes free in the conjugate beam, and the free end in real beam becomes fixed in the conjugate beam. And so, if the beam is like this, then if the conjugate beam becomes this becomes free, and this free end becomes fixed. So, what would be support condition? Support condition for this beam will be this end will be fixed and this end will be free. So, this is A and this is B. So, this is real beam, this is bending moment diagram, and this is conjugate beam. Okay. Now, what next? Next is determine the internal forces in this beam. So, since in this example we are asked to determine deflection and slope at B. So, what we have to find out here, what would be the shear force and bending moment at B, and shear force will give you the rotated slope, and bending moment will give you the deflection. So, first draw the free body diagram of the entire structure. The free body diagram of the entire structure will be this. Apply the load on this, and then fixed end we have, say this is Bx, this is Bx, let us use different pencil, this is Bx, and then this is By and moment M B. Okay. And this is A and this is B, this is B, and this length is L, this length is L. Okay. Now, apply summation of f x is equal to 0, a x is equal to 0. You may pass this step, because just by looking at this problem we can say there is no horizontal force here, and the support condition is also such that the Bx, the horizontal reaction, will be 0, but just for the completeness I am writing it, say Bx will be equal to 0, Bx is equal to 0. So, then take summation of f y is equal to 0, summation of f y is equal to 0, and this gives us By, which is upward direction, so positive as far as algebraic operation is concerned, then plus the entire load is also upward, so that is positive, half into this is PL by EI, PL by EI into L, that is equal to 0. Okay. So, this gives me By is equal to minus PL square by 2 EI. Okay. By is equal to this. Okay. Now, what is MB? Take summation of MB is equal to 0, and MB is positive. So, MB is anti-clockwise, negative, and then this By will not contribute, and then plus this is clockwise, this becomes half PL by EI into L into 2L by 3, and MB is equal to PL cube by 3 EI. Okay. PL cube by 3I. Okay. So, what we know is the shear force at B will be slope at B, bending moment at B will be deflection at B. What is the shear force at B? Suppose By is the reaction at B, and if remember our sign convention was and our sign convention was this. If I write our sign convention somewhere here, if this is a small segment of the beam, then this is clockwise couple, this is positive, and then this is our sign convention positive. Okay. So, what will be the theta b? What will be delta b in this problem? Then delta b, let us write delta b is equal to this. This is PL cube by 3I, and theta b is equal to, or absolute value of theta b if you write, then this becomes PL square by 2 EI. Okay. I am written the absolute value because you keep the sign convention as per your you give the sign as per your convention. So, this is the result. Okay. So, delta b is equal to PL cube by 3I and slope is PL square by 2I. Now, if you remember in earlier methods, direct integration method and moment diagram method, we obtained the similar result. Okay. Now, if we see this example and what is the deflected shape of this beam, then the deflected shape becomes like this. Okay. So, this at this point your slope is 0, and at this point your deflection is this, and you take a tangent at this point, and this tangent, this angle will be the slope. Every time when you determine the deflection, even at any point, try to understand or try to get or by intuitively try to see what would be the probable deflected shape of a beam. Okay, that is and then see that deflected shape is consistent with your with the bending moment you get and the sign convention you used. Okay, this was the first example. Now the second example is this. It is now this example is this is simply this is a simply supported beam, but with an overhang of length L by 2, and then we have a concentrated load and at the tip of the overhang. Okay, what we need to do is we need to determine what is the deflection and slope at point B. Okay. Now, so this is the problem. This point is C, for instance. Say this point is C. Okay. Now let us first find out the bending moment diagram. So you see all the methods that we have been discussing, the bending moment diagram plays a very important role. So you must be very comfortable in drawing bending moment diagram of any beam, and before you draw bending moment diagram, try to understand what would be the bending moment diagram just by looking at the beam based on your intuition, and then check whether your intuition is consistent with the results you obtain from structural analysis or not. Okay, so this is the real beam. Now draw the bending moment diagram. Let's, without any calculation, how can we find out the bending moment diagram? This is point A, this is point C, this is point B. Okay, so point A is hinge support, simply is a hinge, so naturally bending moment will be 0 here, and point B is a tip loaded, there is no externally applied load here, so naturally bending moment will also be 0 here. Okay. Now in between C and B there is no other load. So if you take any section, the bending moment at this section will be due to this force. Okay, this force P. So bending moment, if you take any section, the bending moment will be this force multiplied. If you take any section here, the bending moment at this section will be P multiplied by this distance. Okay, so bending moment is linearly varying between B to C. Now what is the sign of this bending moment? Sign of this bending moment is, by just looking at this diagram, we can say that the deflection of deflected shape, or at least for this part, CB part, will be something like this. So naturally this is hogging. So as per our convention, this is negative. So this between B to C, your bending moment varies linearly, and what would be the bending moment at C? It will be P L by 2, okay, because this is L by 2. So this is bending moment diagram. Again, between these to these there is no other load. So whatever bending moment, if you take any section here, the bending moment at that section will be due to the reaction force here. And what would be that bending moment? This reaction force multiplied by this distance. So bending moment will be linearly varying between A and C. Okay, and since there is no externally applied any moment here, okay, so bending moment will be continuous at C. So what will be the bending moment diagram? Then the bending moment diagram is this. This is the bending moment diagram. Bending moment diagram, and as per our sign convention, this is negative. Okay, so without any calculation, we could draw the bending moment diagram for this. Okay, now let's construct the conjugate beam. Conjugate beam will be the real beam. The length remains same as the real beam. This is the real beam. Okay, and the next step is the bending moment curvature diagram of the real beam will be the loading on the conjugate beam. So curvature diagram will be this by EI. So loading will be like this. This is PL by 2 EI, and this is upward because your bending moment is negative. Okay. Now next, another important part, this support condition. Again, go back to the support condition, the list of support condition what we have, that if the free end becomes fixed, fixed become free, and if you have any support, internal support, that internal support become hinge. Okay. So, let us keep here. So, this is free end. So, this become fixed, and this was this is hinge. So, it remain hinge, and there was an internal support here. So, any internal support, it becomes hinge in the conjugate beam. So, we have one hinge at this point, conjugate beam, an internal hinge at the conjugate beam. This is internal hinge. This is hinge. Okay. Now, we have a beam, this is A, this is C, and this is B. So, in this A, B, C, which is subjected to this kind of loading, and the support conditions are given here. Okay. And the next is to again the problem of kinematics, now reduced to problem of statics. Here we need to find out what would be the internal forces. Now, since we are asked to find out slope and deflection at beta, what we need to find out is what is the shear force and bending moment at point B. Now, you can take the free body diagram of part AC separately, free body diagram of part CB separately, apply equilibrium condition and find out what is the bending moment. You know this. So, we won't do that exercise here. I will just give you the final result. Final result is slope is equal to theta, B is equal to, no, you are asked to do delta C, delta B, that was we are asked, that is equal to P L Q by 8 E I. This is the final result. Okay. So, this is acting downward. So, this is positive. So, what your job is to please verify this. Okay. Now, let us see what would be the deflected shape, possible deflected shape of this beam. Now, let us first instead of see the deflected shape, let us find out what could be the deflected shape here. You see, this part will go down because this will behave as normal regular cantilever beam subjected to tip load. This will go down and there is no load here. So, in order to maintain the, since this is go down, in order to maintain the continuity, this beam will deflect like this. So, if you see, yes. So, this part will go down, and at this point the slope has to be slope has to be continuous, and in order to maintain the continuity, that is this will go down. Okay. It will go down. Now, this is the deflected shape. Again, it is good to for any problem, it is good to see the deflected shape as well. Now, next problem is, we have one more problem, and this problem is this. Okay. The problem deflected shape is already shown here. Now, the problem is this. Okay. Now, it is again first is now here you remember in earlier one of the earlier lecture we introduced the concept of superposition. Since we are linearity is one of the important assumption in all our analysis, we assume that load deflection, the relation is linear, or stress strain relation is linear. So, what we can do is we can divide the problem into small problems and find out the response of each sub problem separately, and then combine them to get the response of the actual problem, and combine them means combine just adding them by algebraic addition will give us the response of the actual system. And this step is sometimes very useful, because suppose in a structure, if you have a very complicated loading condition, there are different kinds of loading. So what you can do that, if you look at each load separately, then probably those loads are not that the analysis with those loads are not difficult, but since they all are acting together, that's why the problem seems to be very complicated, or the calculation seems to be very tedious. So this is one example where we can show how the conjugate, we can demonstrate two things. One is the principle of superposition, and also the conjugate beam theory. Okay. Now suppose this is the problem. Now we have is a fixed end, and then this is roller support and one internal hinge here, and then lengths are given. This problem is taken from the structural analysis book by Hibbeler. This is the load. Okay, and the interesting thing is, you check, there is an internal hinge here. There is an internal hinge here. If you can see, there is an internal hinge here. This is an internal hinge at B. Okay. Now what we do first, we first decompose the problem into two. Let's how we can decompose the problem into two. First is the same beam with this 40 kilonewton load, and then again the same beam with this 50 kilonewton per meter moment. Okay. So the first part is the same beam, one end fixed, and then we have an internal hinge here, and then roller support, and then externally applied load 40 kilonewton. Okay. And this is A, B, C, and this is D. This is first case. And the second part is again the same beam, same support condition, and then an internal hinge here. This is A, B, C, and at C we have additional moment, say this is 50 kilonewton. Okay. Now, so this will be equal to this plus this, this equal to this plus this. Okay, this plus this. What we will do is now find out what is the deflection at what it is asked is what is the deflection at B. And so first from this we find out the deflection at B, from this we find out a deflection at B, and then if this is system 1, this is system 1 and this is system 2, and then delta B1 plus delta B2 will be equal to delta B of the real structure. Okay. Now apply the conjugate beam method. Before we apply the conjugate method, the first thing is we need to find out what is the bending moment and shear bending moment diagram. So again, let us find out, we can do I know that you can do the calculation to find out the bending moment diagram, but let us just by looking at the beam get some idea about the bending moment diagram. Okay. Now, so first draw this beam. Okay, let's first start with this. This is the beam. Okay. Now what we have is okay. Now let us let us see what is the bending moment diagram for this case. At this point the bending moment is 50. Okay. And as per our sign convention, this is hogging moment. So at point C the bending moment will be this. This is minus 50, or minus means it is downward. Okay. Now, you see between B and C there is no other externally applied load here. Okay. So, if we take any section here, so what happened, and also we know that bending moment at B will be 0 because it is hinge. Okay. So, then at any, if you take at any section, then at any section the bending moment, what are the forces that will cause variation of bending moment between B and C. This is the initial moment at B, and then you have a support reaction, and then support reaction will decrease this moment, and eventually at point B your moment will be 0. So, up to at point B your moment is 0. Okay. Now, again between B at A to B there is no other load. Okay. So, this the moment will be, and there is no externally applied moment also. So, the moment will be continuous, the slope of the moment will be continuous, there is no additional external other load here. So, what would be the bending moment diagram? Bending moment diagram will be something like this. Okay. This will be 50, this will be 50, and you calculate it. I am not writing the calculation, this will be 80. Okay. Now, this you can calculate, actually this length is 50. So, anyway, and this length is 8, this length is 5 meter, this length is 8 meter. So, this is the bending moment diagram for this. Now, let us find out what is the bending moment diagram for this. Now, if you take BC separately, you see there is no other external load, here. So, what will happen? What the reaction at C will be 0. Now, the reaction at C will be 0 means there is no bending moment in BC. Even between BD also there is no other load. Reaction at the hinge reaction at B is 0, C is 0, and up to C and D there is no other load. So, naturally between C and D there will be no load, and at you have load 40 kilonewton at D, and between A and D there is no other load. So, the bending moment at any section will be caused due to this load, and the bending moment will be this load multiplied by this distance. So, bending moment will linearly vary between A to D, and what would be the sign of the bending moment? This beam will deflect like this. So, bending moment will be hogging bending moment. So, this is bending moment diagram between D, and this is this length, this is 40 kilonewton, and this length is 4 meter. So, this bending moment will be 160 kilonewton meter. Okay. So, this is bending moment diagram for this part, this is bending moment diagram for this part. Now, let us draw the conjugate, let us find out the conjugate beam. The first step is the loading on the conjugate beam will be the curvature diagram of the real beam. So, loading on the conjugate beam will be, this becomes 80 by EI and this becomes 50 by EI. Okay. This is positive. So, this will act downward, this will act downward, and this will act upward, right. And what would be the support condition? Again, find out the support condition from here. If you see, the roller support remain as roller, and then if you have internal hinge, then internal hinge becomes internal support, and the fixed support becomes free. So, the support condition will be, so this becomes this internal hinge becomes roller, this is fixed. So, this will be free, and this remain roller, or this becomes a hinge, this become hinge, and this remain as roller. Okay. This is the support condition. Okay. Now, let us see what is the support condition for this. This support condition for this will be again same. So, this is roller, and this becomes internal hinge, become external intermediate hinge support, and this fixed end becomes free. And what would be the loading? This loading will be upward direction. This loading will be upward direction. Okay. Now, what we need to find out? We need to find out what is the delta B. So, delta we need to find out what is the delta B1 from here, and then what is the delta B2 from here. Now, let us find out delta B will be the, so this is A, this is B, this is C, A, B and C. Okay. Now, bending moment at B. So, M we need to find out what is MB here, and from this also we need to find out what is MB here. Okay. Now, what is MB? Now, this MB will give us delta B1 and this give us delta B2. Okay. Now, if we then add delta B1 and delta B2, we get delta B, and I will just give you the final result. We get delta B1 as delta B1. Let us give you the final result. So, you can find out what is the delta B1 and what is the delta B2. Delta B is become 427 by EI. by EI. So, now what is the advantage of dividing by what advantage we have by dividing the problem into two? Now, in both the cases the bending moment becomes very simpler. Okay. Without that also we could determine what is delta B, but in that case bending moment diagram would have been this plus this, and this then it will be the variation in a same length will be more. That is why probably this approach the computation becomes, the calculation becomes easier. Okay. So, you can determine, please find out what is the delta B1 and delta B2 and then check whether you are getting these results or not. In addition to that, you also find out what is the slope at theta B. Okay. Now, you see, since it is hinge support, the hinge support does not give you any rotational constraints. So, not necessarily that your slope is continuous at point B. For instance, if you see the animation, this is the deflected shape of this beam, and now you see this point is the hinge point and how they behave. And if you see the deflected profile, deflection is continuous up to this part. It is not only continuous, it is the slope is continuous up to this part. For this part also BC, so slope is separately continuous, but at point B there is a sudden, the slope is not continuous. So, if you calculate the slope for slope at B due to part B AB and slope at B for part BC, those two slopes will not be same. So, you find out what are the slopes from at same point B due to part BA and due to part BC, and the slope will be the, if you get the shear force at here and shear force at here, you add these two shear forces and you will get the slope at point B. Okay. So, well, this was some demonstration of conjugate beam theory. So, there are again many examples given in the book. Please do some examples and make yourself comfortable with the concept. So, next class what we will do is we will see briefly review the internal forces in statically determinate frames. Okay, then see you in the next class. Thank you.